right, hello students. Today we are doing lesson 4, so 8.4, and today is all about a dilation. You should be on page 465 of your book. Now, when you think of dilation, you might think of like your pupil, where if you were to close your eyes and then you open them in a bright room, you can watch your pupil dilate, right? Or somebody shines a flashlight in your eye, you can watch it get bigger or smaller, because that's what's allowing how much light your eyes need. So if they're getting bigger, because you're trying to allow more light in, if it's very bright, your pupils get very small, they don't want to let in a whole lot of light. So larger and smaller, we're going to take our shapes and make them larger, or we can make them smaller, is what we're going to be doing today. So let's start off here. A few examples. I'm not going to go through all of them. I think after a couple examples you're going to get, it's one of the easier ones, I feel. So for this, again, dilation is a lot like kind of like scale factor. Microscopes in large objects that are too small for the human eye to see. Some microscopes actually can magnify it up to 1,000 times its size. So maybe looking at a cell, very, very, very small, looking at something, making it larger. We're going to take a shape, make things that are small bigger, or things that are bigger, making them smaller. Our standards. Okay, center of dilation. Now, for every example you should be doing, the center of the dilation will be the center should be at the origin. If we don't go about the origin, it's definitely harder, but every question we're going to go through is going to be dilating from the center, getting larger or smaller from the actual origin. The dilation, that is actually the thing going larger or getting smaller. The scale factor is how much larger or smaller is it getting. That's what we'll be working on today. So if we want to find out the actual scale factor of the dilation, what we need to know is if we look at this, I know it's very small to see, it has basically your C prime, B prime, so we're just going how long is side CV? So that's just a side CV. That is 4. We put that over side CB. So what you'll notice is we do the image divided by the original. The image divided by original. So that was 4 over 2. So we could say the scale factor is 4 to 2. I could also write it like this, 4 to 2. But we should try to reduce if we can. Well, what's the same as 4 to 2? 4 over 2 would be a 2, which means that our original size, shape, everything was times 2. It got twice as big. It was 1, it became 2. It was 2, it became 4. Everything doubled in size. We dilated it by a scale factor of 2. Since our scale factor is greater than 1, it's going to get enlarged. If our scale factor is less than 1, like a fraction, 1/2 or 3/4, then it's going to be getting smaller or reduced. For this example, again, we want to do the image over the original. So in this case, the image, remember you're always looking for those little prime bars right there. The only thing we know is that this right there is 6. I put that over the original 8. I could write 6 to 8 this way, but we can reduce that, right? What goes into both 6 and 8? 2. That would be 2 or 3 to 4. What am I doing? 3, 2, 4. You could also write 3 to 4 this way. So whether it's a fraction or 2 dots, doesn't really matter, but 3 to 4. So this would be getting smaller. We went from one size, we shrunk it down. This is less than 1, so we know that it's going to be reduced. Same thing before. Okay. Make sure that that's number 4 here, page 4. Yep. I don't really like this example. I'm actually skipping the first couple here. I didn't like them when I was working with them. It didn't work out very well. It's a hard time. I can't move this to the halfway point. It automatically goes to 6 or 5. So I had to skip this. Not sure what's going on with the board, but it won't let me go half. So I'm going to end up skipping past that one. the words we're using. When the center of the dilation is the coordinate plane is the origin, each coordinate of the preimage is multiplied by a scale factor of k to find the coordinate of the image. Now, the last time you probably worked with k would be the direct variation. If you remember a long time ago when we did direct variation, y equals kx. Basically, your k was what is the same thing known as your slope. What is it changing by? How much is it changing by? Direct variation. Same kind of thing here. We are going to be changing by a scale factor of k. That means what are we going to be changing to? Your variable-wise, it's very easy. It's very easy. You are at xy, it's going to become kx, ky. All that means is we're going to take the x value times k and the y value times k to get our new coordinate. So if you were adding to your note card, you could write for a dilation, you go from xy to kx and ky. On your graph, if you look at it, if we had a scale factor of 2, so we were at, let's say, 1, 1, if I have a scale factor of 2, I would take both those numbers times 2. So it would become 2, 2 instead. Everything is just multiplied by a scale factor of 2. So that 2 is the place of the k. Okay, so if you look at this one, when you have a dilation of scale factor larger than 1, it will be a larger image. When we have a scale factor that would be less than 1, we have a reduction. It's going to be smaller when we get done. Now, what if you have a scale factor of 1? Well, then it's the same thing. Notice how A and A prime are in the same place. Well, if you had a scale factor of 1, it didn't change because everything times 1 is itself, so it didn't change. You would just put the same image over the original. It didn't change, or it dilated with a scale factor of 1. No change. What would happen here? If I had a scale factor of 2/3, would that be enlarging or reducing? Reducing, it's less than 1. What about 6? Obviously enlarging. How about a scale factor of 1? None. It doesn't get bigger, it doesn't get smaller, it stays the same. Okay, we have these vertices, A, B, and C. We want to do a dilation with a scale factor of 2. Very easy. We know that when we're doing a dilation, my x, y will become my k, kx, and ky. So all we have to figure out is what is my k. So I'm going to start over here. It's k. I'm going to figure out what is the scale factor. Well, in this case, my dilation scale factor of 2. So this would become 2x and 2y. Now all we have to do is figure out what are the x and y. So let's just look at A. A started out with as -2, 1. If I'm going to take everything times 2, well, my A prime would then become -4, +2. All I do is take this number times 2 and my y times 2. Pretty simple. And my B original was at -4, 5. So B prime would become -8, 10. And then my C original is 3, 2. So my C prime would become 6, 4. And then you would plot that point. Everything doubled in size. Scale factor of 2. We just did all that in the previous page. Again, for some reason, I can't end up putting dots on except for my ink. It doesn't really push. It's supposed to put a point on there and it graphs it. It's not working for me. Don't know what's going on with this, so I have to kind of skip through these. I'm going to skip the 2.5 one. I don't believe any and Alex are going to be decimal values. We couldn't do it, but I wanted to get to this one where now we're going to do a 1/2 instead. So here we know that to do a dilation, we go from x, y, and we go to scale factor of k, x, and ky. In this case, what I'm doing is I'm going from xy into 1/2 x and 1/2 y. Everything is becoming with a scale factor of 1/2. So if we look at J is at 3, 8. J prime would then become half of 3, 1.5, and half of 8, 4. My K original was 10, 6, so my K prime would become half of that number 5, half of that number 3. And my L original was 8, 2, so my L prime would become 4, 1. Pretty simple. You plot that, everything got reduced, half the size. Just did all that. And another one of those. And I still can't do these. Okay, what if you were trying to describe the dilation? Figure out what is the dilation. You want to remember that we are going to be using that fraction, and it is going to be the image over the original. The image, remember you're looking for these, just pick a side if you wanted to. Is there any side that you know how long that side is? Well, looks like we might have to use the Pythagorean theorem here. So if we look, I know if I'm going to pick, let's just say this side right here. I'm going to go with CB. I look, I go 1, 2, 3, 4. So this side of the triangle is 4, and I go up 1. I go up 1. So I know I can use Pythagorean theorem right there to see how long that is. We would know that 1 squared plus 4 squared is equal to then c squared. So 1 plus 16 equals c squared. So the square root of 17 is equal to c. Now, let's leave that right there. The image is the square root of 17. That's how long this side is. Let's do the original. If I do the original, then I could do, let's do, how about black? I'm looking for this side right there. So 1, 2, 3, 4, 5, 6, 7, 8. So I know that the bottom is 8. And I go up now, I have to go up 1, 2. So I need to know that. So I would know 8 squared plus 2 squared. So I'll do that right here. I would do 8 squared plus 2 squared equals my c squared, or my hypotenuse. So that would mean that 64 plus 4 equals c squared. So I would have the square root of 68. So if I do square root of 68. Now, let's say I actually did that on a calculator. What if I did that right there? If I take the square root of 17 divided by the square root of 68 equals, I get exactly 0.5. So it looks like weird numbers, but it worked out where I know my scale factor is 0.5. So this is a dilation of 0.5. Now, we realize that from the original, it got smaller. We know we did it right. This is less than 1. So I would keep these as exact and use the exact numbers in a calculator, and it works out. Now, let's go to your assignment, because I think you're going to understand that that'll be the hardest thing that you would have to do. Let's take a look. 8.4. Looks like we're doing 15 questions, I believe, on this one. For the figure below, do a dilation centered at the origin with a scale factor of 3. So what we can do, you can use your mouse down here, and I am going to move that little slider to the dilation they told me. I want a scale factor of 3, so I go up 2, up to 3. You see how it gets larger every point. So instead of being at 4, 4, well, if I took that times 3, I would be at 12, 12. They just moved it up bigger, and it goes farther away from 0. So, endpoints of original figure. On the left side, what was the original point? Well, the left original was at 1, 5, so I'll put that in here. It's at 1, 5. The right side of that was at 4, 4, so I'll put that in there, 4, 4. Now, the final figure, the left point is now at 4, 15. 4, No, 315 should be. 315. And then my last point right there, you can see it's at 12, 12. And we can double check where if I had a scale factor of 3, this is times 3, that's times 3, this times 3, that times 3. Number 2. Number 2, for the figure, do a dilation centered at the origin with a scale factor of 3, then answer the question. Again, I can take this shape and I can do the dilation right there. So I'm going to do my dilation. It says 3, so I'm going to move the little slider over to 3. And you can see the original, the image. The longest side of the original figure. Well, the long side would have been that top side. So how many units is it? You can see it's only 2 units long, so I'll put 2 there. Longest side of the final figure. Well, we have 1, 2, 3, 4, 5, 6. Should have been. It should have been 3 times larger. Oh, well, I wrote it 3 times larger. Fill the blank to make the true statement. The longest side of the final figure equals blank times the longest side of the original figure. So I'm going from the final figure to the original. What would I have to multiply to go from the 6 to the 2? 1/3, right? I have to take this times 1/3. True or false? A dilation with a positive scale factor greater than 1 gives a final figure smaller than the original. That is false. True or false? The original figure and the final figure are similar. Similar. The word similar means the same, like the same ratio, but it could be bigger or smaller. Yes, a dilation is always similar. It's taking the same shape, making it bigger or smaller. The angles stay the same, but the side lengths would always have the same ratio. That is a true statement. What happened there? I'm thinking about this, but this is weird. The longest side of the final figure, well, the final figure equals, oh, I thought it was going here times that. I didn't know it was this. Okay, that seemed weird. I thought this should have been 3. Let's get rid of this. I thought it should have been 3, but I thought they were trying to take this times that. It's this times this. There we go. Now let's check. There we go. Okay, so I don't know why they're trying to switch it around. Watch the wording on that one. Okay, do a dilation of the center of the origin with a scale factor of 3. 3 again. Okay, so move the slider over to 3. There it is. Figure out how many square units of the area. Let's take a look at the area now. This might be interesting. If we look, area of the original figure. If I have a 2 by 1, what's the area? I take 2 times 1 and you get 2. So we have 2 square units. Now, the final figure. I'm 1, 2, 3, 4, 5, 6. So this would be a 6 by 3. What is that? 18. So I went from 2 to 18. Why is that? Down below. Fill in the blank to make a true statement. Area of the final figure equals blank times the area of the original. How would I go from 2 to 18? What would I take that times? It's 9. Do you know why it's 9? Well, let's think about it. If we go from one size to a larger size, and this was a 2 by 1, and we became a 6 by 3, what happened was I took this side times 3, and I took this side times 3. When you do area, we do length times width, so it's 3 times 3, which is 9. So when I double both sides, I end up, or tripling both sides, I end up becoming 9 times larger, because each dimension got 3 times larger, and 3 times 3 is 9, so this one would be 9 times larger. Down below, true or false? The original figure and the final figure are similar. That is a true statement. Number 4. Draw an image of the following segment after dilation centered at the origin with a scale factor of 3/2. So we need to know the endpoints. So if I were to put a point right there and a point right there, let's just say A and B to make it easier to see. A is at 6, 12. So A is at 6, 12, and then B is at 10, 12. B is at 10, 12. Now, to get to my A image, I need to take my X times that number. So I'm going to take 6 times 3 over 2. Now, think about when we did fractions. Before I multiply across, let's look diagonally. 2 goes into 2 once, 2 goes into 6 3 times. 3 times 3 is 9, 9 over 1, so I know 9 is the first one. Same thing here. I'm going to do the same with the 12. Okay, that would be 12. Oh, I'm going to put the 3 halves first. I'm going to put 3 halves times 12 over 1. Again, if I'm multiplying, look diagonally. What can you cross out? 2 goes into 2 once. 2 goes into 12 6 times. 6 times 3, 18. So my A image, A prime, would be 9, 18. This is more than 1, so it will get larger. And my B, do the same thing on B. B prime, I'm going to take my 3 halves times 10, which would be 10 over 1. I can divide out 2 goes into 2 once. 2 goes into 10 5 times. 5 times 3, 15. So my B prime would be 15 for my X value. I'm doing 12 again. Well, I already did 12 once. 12 ended up giving me 18. So why do it again? I know it's 18. So I'm going to plot those points on there. I want 9, 18. So I'm going to put a point at 9 and 18, which would be right there. Yep. My second point was 15, 18. So then I'm going to go 15, 18. Need my pencil. I go to 15 and I go up to 18. Right. 50. No. Should be 15 and 18 right there. There we go. Now I connect the dots. It's 1.5 times as much. And should be one new one. Same 5 questions. The dilation, center at the origin with a scale factor of 2/3 is applied to triangle RST. So we can see the original RST. They did a dilation less than 1, so it got smaller. There's a result. So what are the new chords? You have 2 options here. You can do the math if you would like. By doing the math, meaning you're going to take every single number times that and figure out what the answer is, or you could also look at this and put that in there, right? So whichever way you think is fastest. If you want to do the math and take -9 times 2 over 3, 3 goes to 3 once, 3 goes to 9 3 times, 3 times 2 is 6, so -6. That would be where I would put that right there. And then I'm taking 6 over 1 times 2/3. 3 goes to 3 once, 3 goes to 6 twice, 2 times 2 is 4. So my first point would be -6, 4. So I could type that -6, 4, just like that. Now, you can do the rest of them. What happened here? You took everything times 2/3. So you want to make sure it says 2/3 x, 2/3 y. So the only one that says 2/3 x, 2/3 y, but make sure they're in the right order. 2/3 x, 3 halves. Nope, not that one. I don't want that one. I want 2/3 x, 2/3 y. 2/3 x, 2/3 y. This is the one I want. So be careful. They do kind of try to trick you a little bit with that one. And then if we go back to 6, I believe 6 should be just like number 1. There it is. So you have 15 questions, the same 5 questions 3 times over. Good luck, and I will see you on Tuesday.